every type of cosmic radiation. Space is complicated. We make it simple. Space isn't empty. It's soaked in radiation constantly from sources scattered across the entire observable universe, and almost none of it is the kind of radiation most people picture when they hear the word. Some of it has been traveling since almost the beginning of time itself. Some of it is energetic enough to punch through several meters of solid lead. We're going in order from the faintest, oldest signal to the most violent, most recently discovered one. Then we'll sort them a second way by how dangerous each one actually is to a living human body. Because on this list, constantly bathing the Earth and actually a threat to you are two very different categories. The cosmic microwave background. We begin with the oldest light in the entire universe and also the faintest entry on this list by a massive margin. Roughly 380,000 years after the Big Bang, the universe cooled enough for light to travel freely for the first time, instead of being constantly scattered by a hot, dense fog of charged particles. That first burst of freed light has been stretching and cooling ever since, as the universe itself has expanded, and today it arrives at Earth not as visible light at all, but as faint microwave radiation, at a temperature of just 2.7 degrees above absolute zero, arriving from every single direction in the sky simultaneously. Here's the fact that should genuinely bother you. You have personally witnessed this radiation without knowing it. A small percentage of the static visible on an old analog television tuned to an empty channel was caused by this exact signal. Photons from the early universe, older than every star, every galaxy, and every atom heavier than hydrogen and helium, striking your television's antenna and briefly appearing on your screen as random noise. Here's the part that changes everything about how astronomers use this signal. Tiny temperature variations within the cosmic microwave background, differing by only millionths of a degree across the sky, are essentially a baby picture of the universe, mapping the exact density fluctuations that would later collapse under gravity to form every galaxy, star, and planet that exists today, including the one you're standing on right now. Solar radiation and the solar wind. Here's the twist. The nearest, most constant source of radiation in your daily life isn't some exotic deep space phenomenon. It's the star you evolved next to. The sun constantly emits a stream of charged particles called the solar wind, along with bursts of X rays and ultraviolet radiation, all of which would be lethal to unprotected life on Earth's surface if our planet didn't have two separate layers of defense working simultaneously. A global magnetic field that deflects most charged particles around the planet entirely, and a thick atmosphere that absorbs most of the remaining high energy light before it ever reaches the ground. Here's the fact that should genuinely bother you. During major solar flares and coronal mass ejections, the sun's radiation output spikes dramatically, and astronauts aboard the International Space Station, orbiting above most of the atmosphere's protection, sometimes have to shelter in more heavily shielded sections of the station during the most severe events. Mars, which lost its global magnetic field billions of years ago, receives dramatically more surface radiation than Earth as a direct result. A future crewed mission there would need to factor solar radiation exposure into mission length as seriously as food or oxygen, because on Mars, the sky itself is quietly, continuously dangerous in a way Earth's sky simply isn't. Jupiter's radiation belts. Here's the fact that reframes how special Earth's own radiation environment actually is. Earth isn't the only planet with trapped radiation belts, and it isn't remotely the worst one. Jupiter, with a magnetic field roughly 20,000 times stronger than Earth's, hosts radiation belts so intense that they represent one of the single greatest engineering obstacles to exploring the planet up close. Here's the number that should genuinely bother you. A human standing unprotected near Jupiter's moon, Io, deep inside the planet's radiation belts, would receive a lethal dose of radiation in a matter of minutes, and even heavily shielded spacecraft have to carefully plan their trajectories to minimize total exposure time. NASA's Juno spacecraft, currently orbiting Jupiter, carries a specially designed titanium vault, essentially a small radiation-shielded room built around its most sensitive electronics, specifically to survive repeated passes through the belts long enough to complete its science mission. Here's the part that lingers. Jupiter's radiation environment is intense enough that it's considered one of the primary reasons a crewed mission to the Jovian system remains, for now, essentially off the table, not because we can't reach Jupiter, but because we don't yet have a practical way to keep a human crew alive once they arrive. Galactic cosmic rays. Here's the reframe: this category isn't from our sun at all. It's debris from explosions that happened elsewhere in the galaxy, sometimes long before the solar system even formed. Galactic cosmic rays are extremely high energy particles, mostly protons, accelerated to a meaningful fraction of the speed of light by the shock waves of ancient supernova remnants, then sent wandering through the galaxy for millions of years before some of them happened to strike Earth's atmosphere. Here's the fact that should genuinely unsettle you. These particles carry so much energy that when one strikes the top of Earth's atmosphere, it triggers a cascading shower of secondary particles, sometimes numbering in the billions, raining down toward the ground from a single initial collision, meaning a fraction of the particles passing harmlessly through your body right now started as one single proton, flung out of a dying star that happened to hit an air molecule directly above your head. Astronauts outside the protection of Earth's atmosphere and magnetic field are exposed to significantly more of this radiation than anyone on the ground, and it's currently considered one of the most serious unsolved engineering problems for any future crewed mission to Mars. Unlike solar radiation, which spikes and fades in identifiable bursts, galactic cosmic rays arrive as a constant, low level bombardment for the entire multi year duration of the trip, difficult to fully shield against without impractically heavy spacecraft walls. Gamma ray bursts. Here's the pivot. This is where the category stops being background noise and starts being a genuine, if rare, existential concern. Gamma ray bursts are the most energetic electromagnetic events known to occur anywhere in the universe, typically caused by the collapse of an extremely massive, rapidly spinning star directly into a black hole, or by the merger of two neutron stars. Both events capable of launching narrow, tightly focused jets of gamma radiation at nearly the speed of light. A single gamma ray burst can release more energy in a few seconds than the sun will produce across its entire 10 billion year lifetime. And because the radiation is focused into narrow beams rather than spread in every direction, a burst can appear briefly, blindingly bright across billions of light years, even though the total energy involved is concentrated rather than universal. Here's the fact that should genuinely bother you. Some researchers have proposed that a gamma ray burst pointed directly at Earth from within our own galaxy, a low probability but not impossible event, could severely damage the ozone layer within seconds. And one specific extinction event, roughly 445 million years ago, has been proposed, though not confirmed, as a possible candidate for exactly this kind of cosmic strike. Here's the part that lingers. Because the beam is so narrow, a nearby gamma ray burst could go off, devastate a planet on the other side of the galaxy, and Earth would have no way of knowing anything catastrophic had even happened, unless we happen to be standing directly in the beam's path. Ultra high energy cosmic rays. Here's the fact that should genuinely bother astrophysicists specifically. Some cosmic ray particles arrive at Earth carrying more energy, packed into a single subatomic particle, than a professionally thrown baseball. An amount of energy that, by all current models of particle acceleration, shouldn't be physically achievable by any known astrophysical process. These are called ultra high energy cosmic rays, and their source remains one of the most stubborn open mysteries in modern astrophysics. Leading candidates include the violent environments around active supermassive black holes and the aftermath of the most extreme gamma ray bursts, but no confirmed source has ever been definitively traced for the most extreme individual events recorded. Here's the part that changes how difficult these are to even study. Because they're so extraordinarily rare, some of the highest energy examples arrive at a rate of roughly 1 per square kilometer per century. Detecting enough of them to study statistically requires astronomers to build detector arrays spanning thousands of square kilometers of open desert or ice, essentially turning entire landscapes into passive particle detectors just to catch a meaningful sample of events that arrive individually once in 100 years per patch of ground the size of a small town. Van Allen radiation belts. Here's the fact that closes this list by bringing it back home. Not every dangerous radiation zone on this list is somewhere distant. Earth itself hosts two donut shaped belts of intensely energetic charged particles trapped and held in place by our planet's own magnetic field, extending from a few hundred to tens of thousands of kilometers above the surface. These particles, mostly protons and electrons captured from the solar wind and cosmic rays, are funneled and concentrated by Earth's magnetic field into these two distinct bands, with a relatively safer gap between them. Here's the fact that should genuinely bother you. Any spacecraft or astronaut passing through the belts is briefly exposed to intense radiation, which is precisely why Apollo mission trajectories to the moon were deliberately planned to pass through the thinnest, least dangerous sections of the belts as quickly as possible, minimizing exposure time to a matter of a couple of hours rather than lingering. The belts aren't static either. They visibly swell and shrink in response to solar activity, sometimes forming brief temporary third belts during intense solar storms, meaning the radiation environment immediately surrounding our own planet is an active shifting hazard, not a fixed permanent structure at all. Solar particle events and astronaut health. Here's the fact that closes this list on the most immediately human note. Setting aside the exotic categories above, one of the most practical ongoing concerns in modern spaceflight is the simple accumulated radiation dose astronauts absorb over a career. NASA tracks career radiation exposure limits for every astronaut individually, calculated to keep their statistical increase in lifetime cancer risk below a defined threshold. And a single severe solar particle event, an intense burst of high energy protons from the sun, can deliver a meaningful fraction of an astronaut's entire career limit in the space of just a few hours if they're caught unshielded outside a spacecraft's more protected sections. Here's the fact that should genuinely bother you. An unshielded astronaut caught during a worst case solar particle event while performing a spacewalk or on the surface of the moon or Mars without adequate shelter could theoretically receive a dose sufficient to cause acute radiation sickness within hours, which is precisely why lunar and Martian habitat designs increasingly plan for a dedicated, heavily shielded storm shelter module, sometimes as simple as a small chamber surrounded by stored water or Martian regoliths specifically reserved for these unpredictable events. Here's the part that lingers. Unlike galactic cosmic rays, which arrive at a slow, predictable, constant rate, solar particle events can develop and peak within less than an hour of the initial warning signs, meaning any future crew on the Martian surface will need a functioning early warning system and a fast enough evacuation plan to reach shelter before the worst of a storm actually arrives. Here's a fact worth sitting with before we sort this list. Almost every category above was invisible to astronomy for most of human history, purely because none of it comes as visible light. Radio waves, X rays, gamma rays, and the specific microwave signature of the cosmic background all sit outside the narrow band of the electromagnetic spectrum human eyes evolved to detect. And every single one of them required a dedicated, purpose built instrument, often only developed in the last 100 years, to even confirm existed at all. The cosmic microwave background wasn't detected until 1965, and it was found essentially by accident by two radio engineers trying to eliminate a persistent, unexplained hiss of noise in their antenna, initially suspecting pigeon droppings on the equipment before realizing they'd stumbled onto the oldest light in the universe. Ultra high energy cosmic rays weren't confirmed until dedicated detector arrays were built specifically to catch them, decades later still. The universe has been broadcasting on nearly every one of these channels for its entire existence. We only started listening on most of them within the last century. Let's sort these 8 again, a different way, not by how they were discovered, but by how dangerous each one actually is to a human body. On the constant but harmless end, the cosmic microwave background, a real measurable signal from the edge of time itself, and yet so faint it poses zero danger to anything ever. On the manageable with shielding end, solar radiation and galactic cosmic rays, genuinely hazardous over long-term exposure, but survivable with the right engineering, exactly the problem current spacecraft designers are actively solving for Mars missions. On the acutely dangerous if close end, the Van Allen belts, intensely radioactive in a localized, well mapped region we've learned to navigate around rather than through. On the catastrophic but improbable end, gamma ray bursts, capable of ending complex life on a planet, but statistically rare enough that no confirmed strike has hit Earth in the entire fossil record with certainty. And on the genuinely mysterious end, ultra high energy cosmic rays, individually more energetic than anything else on this list, and yet so rare and so poorly understood that we still don't confidently know where a single one of the most extreme examples actually came from. It's worth remembering before we close exactly how thin Earth's two-part shield actually is compared to the scale of what it's blocking. The atmosphere that stops most incoming radiation is only about 100 kilometers thick before it thins into effective vacuum, a distance you could drive in about an hour on a highway if roads went straight up. The magnetic field that deflects the solar wind around the entire planet is generated by a churning ocean of molten iron a few thousand kilometers beneath your feet, a process that could theoretically weaken, shift, or even briefly reverse polarity over geological timescales, as Earth's magnetic field is already known to have done many times in the planet's 4.5 billion year history. Neither shield is a permanent, guaranteed feature of this planet. Both are ongoing, active processes, and every form of radiation on this list is only ever one geological hiccup away from reaching the surface far more directly than it does today. Here's the last thing worth sitting with. Every single second, your body is being struck by radiation that has traveled from the edge of observable time, from the heart of our own sun, from supernova remnants scattered across the galaxy, and occasionally from sources so extreme that physics still can't fully explain how they exist. Almost none of it does you any harm, purely because Earth happens to sit behind two separate, ordinary seeming shields, a magnetic field and an atmosphere, that most planets in the universe simply don't have. Not bad for stick figures on a rock.